warm dark matter and self-interacting dark matter. And then I'm going to wrap up very briefly by mentioning non-particle dark matter. So update on questions. I've added answers to 3 new questions on the Padlet website. The first is one that was posted up there by someone, and then the second 2 are questions that were asked yesterday, but where I thought it was useful to post some links to papers that would expand on the answers that I gave yesterday. Okay, so small scale challenges. So this is a topic that if you'd like to know more, it's the focus of the Bullock and Boyle and Colchin review paper that I flagged up yesterday and will flag up again today as useful reading. And I expect that this is something that Anna Kapita is likely to talk about. So broadly, this is referring to discrepancies between the expectations for cold dark matter from simulations and observations. And this is something that started emerging in the late 1990s. And historically, it was referred to as a small scale crisis. But as we'll now see, that's probably over-exaggerating the situation. And so here I'm using what the phraseology of these 2 guys was, small-scale challenges, as in there are potential issues, but it's not a crisis. There are 3 of these. The first 2 are the historical ones, and then the third one is a slightly more subtle thing which emerged subsequently. So the first of these issues is what's called the cusp core problem. And this is something we've already talked about a bit. And this is regarding the density profiles in the inner regions of dark matter halos. And as we saw yesterday, simulations containing just dark matter produce halos with what are called cuspy inner density profiles. So they rise steeply in the inner regions. However, observationally, it seems that galaxies, and in particular small dark matter dominated ones, have much shallower inner density profiles and possibly even sort of tending to a constant, which is known as a core. So that's the cusp core problem. There's then one which we haven't talked about so far, and that's the missing satellite problem. So we have seen pictures from simulations that simulated Milky Way size halos contain huge amounts of smaller subhalos within them. And so a Milky Way size halo would typically contain of order 1,000 dwarf galaxy size subhalos. As of sort of 20 years ago, there was only of order 10 dwarf galaxies observed within the Milky Way. But what people have done subsequently is managed to find lots and lots of very dim dwarf galaxies, things with only, a handful of stars, so they were hard to find. But the situation we're at now is we've got more of these dwarf galaxies, but there's still only about 50 of them observed in the Milky Way. Although one point that has to be emphasized here, though, is that these observations are incomplete because these things are so dim and you can't look everywhere. Not all of the dwarfs that exist have been observed. And then finally, the third of these problems is something called the too big to fail problem. Now, you could potentially explain the missing satellites problem by saying, well, actually, there comes a point where a dark matter halo is so small it gets hard to form stars, and that's why there aren't as many small dwarf galaxies as we think there are dark matter subhalos. However, when you start sort of trying to work out what size galaxies form in what size halos, it turns out that actually you end up with a deficit of medium-sized galaxies as well, things of about 10 to the 10 solar masses. And that's much harder to explain with this little halos just don't do a good job of forming galaxies. So this is one of those things, I'm not an expert on this, but it is a hot topic. So I've tried to give you a brief overview so you've got a feeling for what the issue is and pointed out where you can go to find out more from the experts. As should hopefully already have been apparent from yesterday, to some extent, these discrepancies are because baryonic physics is important and people are really struggling to do the difficult job of correctly modeling the baryonic physics. And as we talked about yesterday, there's some evidence that when you add baryons in, at least in small dwarf galaxies, you do then in your simulations end up with a core rather than a cusp. But that's very much something that's difficult and ongoing. The other possibility, which then relates to what we're going to be covering later today, is that actually maybe it's telling us something about the dark matter, and maybe the dark matter isn't simple vanilla cold dark matter, it's cold dark matter or warm dark matter with some sort of additional interactions. So to wrap up what we've talked about in this last subsection, in simulations, dark matter halos have these cuspy NFW or ionasto density profiles and have lots of substructure, so in particular subhalos, with more subhalos at large radii than at small radii. However, absolutely crucial to factor in what the baryons are doing. This is very much sort of an ongoing work in progress, huge field. What people are finding then is that to some extent density profiles get steepened by baryonic contraction as the baryons fall in. However, you do get these small constant density cores in the inner regions, in particular in dwarf galaxies and possibly in Milky Way size ones too. In terms of the local velocity distribution, that's important for lab-based detection experiments. It seems that the Maxwellian of the standard halo model is an okay assumption, but it seems that there are some features in the high-speed tail that we saw yesterday from material that just hasn't had time to sort of get mixed up thoroughly. And then also in the hydrodynamic simulations, fewer subhalos survive in the inner regions. Obviously, it's crucial to understand the real Milky Way that we live in. And so I've talked about the determinations of both the local density and the local circular speed. And in large part, thanks to the great data from Gaia, there are now determinations of these quantities with very small statistical errors. But the thing to bear in mind here is that the systematic errors are larger, and then there's significant scatter then in different determinations. And these values that seem to be coming out are a little bit higher than the standard values that sort of are traditionally used, but the difference is fairly small. And then the other thing that comes in is the local escape speed, which is where, we truncate the velocity distribution because we think higher speed particles won't be gravitationally bound to the Milky Way, and that's somewhat harder to measure. Over the last sort of decades and in particular years, observations have also found sort of substructure within the Milky Way halo in the stars they can observe in the form of tidal streams, and also this Gaia Enceladus sausage, which is a much more spread out spatial structure, but nonetheless it leads to features in the velocity distribution. And then finally, as we sort of already mentioned, it seems observationally that the inner slopes of density profiles are a bit shallower than NFW, in particular for small dwarf galaxies. So that's the distribution of dark matter finished. I'll pause now in case there are any more questions about this.
Yes, Catherine.
So I remember, this is just a general question about simulations. You said that the way that simulations are done, or they're run for the first time with large particles, I'm not sure exactly what they're called in the simulations, but large chunks of matter, I guess. And then they get smaller, the simulation gets more precise as the particles get smaller. Is the only reason that you can't get down to like actual baryon size or actual particle size computing power? Is there some physics reason that the simulations can't run with particles on that scale?
So the real issue literally is computing power. And again, this is something that Annika will talk about in lots of detail, but what essentially M-body simulations are doing, and the hydrodynamic ones are even more complicated, is for every pair of particles in the simulation, you're adding up the force between it and every other single particle. And it's actually more clever than that. You actually only do the calculation for the nearby ones directly, and you use approximate methods for the more distant particles where the force is small. But the bottom line is you're just adding up lots and lots of forces. So computational power in terms of how many particles you can include really is the huge underlying issue here.
Gotcha. So I bet simulation people are excited about quantum computing.
I don't know. Ask Annika that one.
Any other questions? I don't see any, and there's nothing in the chat. Okay.
Right, so in that case, we can move on to the sort of final topic of constraints from astronomy and cosmology on the properties of dark matter. And what I'm going to focus on is how particle interactions of the dark matter, i.e. deviations from vanilla collisionless cold dark matter, affect the dark matter distribution, and then consequently how astronomical observations can probe that. Depending on how you define astronomy, another way which you can probe dark matter via astronomical observations is WIMP indirect detection, looking for the annihilation products, gamma rays, antimatter. I won't say anything at all about that because that's going to be the topic of Tracy Slatier's lectures. And so, as I already mentioned before, we're going to look first at warm dark matter, then at self-interacting dark matter, and then finally a very brief comment on non-particle dark matter, i.e. you can have dark matter that in fact isn't a fundamental particle. Recommended reading here, it's a shorter list. When writing this lecture and getting up to speed with what the current situation was, I found this white paper by the LSST Dark Matter Group really useful. Anna Capita has, with Matt Buckley, written a review paper on gravitational probes of dark matter physics. This small scale challenges review paper is also useful again because the possible solution to these small scale challenges is particle interactions of dark matter. And then specifically for self-interacting dark matter, there's a physics reports review on that. It's a few years old, but as far as I could tell, there's not been any significant changes since then. So some generalities before we look at particular things. And so this is a distinction that the Buckley and Peter review makes, but I think it's probably useful. That particle interactions can give you deviations from vanilla CDM in sort of two generic sort of broad ways, primordial and evolutionary. And so primordial is when you've got some interactions that change how the density perturbations initially evolve. And so if you change that, you then change the halo mass function that initially forms. On the other hand, evolutionary deviations are what happens once you've formed your halos and then dark matter sort of interacts within them. And as we'll see, the sort of changes you can have there is sort of modifying density profiles of individual halos, modifying the mass function of subhalos and their radial distribution, and also changing the shapes of halos, which is something that we haven't mentioned up to now. There are various possibilities here, and I'm just going to focus on the two that are most widely studied as examples. And so that's warm dark matter and self-interacting dark matter. Other possibilities are sort of dark matter that interacts with baryons, and then a big one is fuzzy dark matter, which is the focus of Lam Hui's lectures. So let's start with warm dark matter. So when we looked at structure formation, we made the distinction between cold dark matter, which is non-relativistic when it decouples, and hot dark matter, which is relativistic. And we already saw from structure formation that hot dark matter is ruled out as being the dominant component of the dark matter because it has this property of free streaming, erasing density perturbations on scales up to galaxy clusters. So the hot dark matter, you'd get galaxy cluster sized objects forming first and then fragmenting into smaller things, whereas actually observations of galaxy clustering match pretty well what we expect from cold dark matter, with small things forming first and then building bigger things via merger and accretion. Warm dark matter is an intermediate case. Neither cold nor hot, is sort of semi-relativistic in the middle. And typically, it's something to get to that, you need things with mass of order of keV. And so you end up with a small velocity dispersion today, but not zero. And a concrete candidate is the sterile neutrino, and I will leave you being told about the particle physics of what a sterile neutrino is. That's Joachim Kopp's lectures at the end of the school. So let's have a look at how warm dark matter affects the primordial power spectrum. So it will free stream and erase structure, sort of initial density perturbations in the same sort of way that hot dark matter does, but just on much smaller length scales. And so hence the cutoff as to what the smallest dark matter halos that form are is smaller than it would be for hot dark matter. And in particular, depending on the mass of the warm dark matter, this cutoff is at about 10 to the 10 solar masses. And so a technical point here, which I'll mention so you're aware of it, is these sorts of calculations are most simply done for what's called a thermal relic, so something that was in thermal equilibrium in the early universe. It turns out that for sterile neutrinos, things get a little bit more complicated, and the effects on the density perturbations and hence the cutoff in the power spectrum and hence the cutoff in the mass of dark matter halos depends on the velocity distribution of the sterile neutrinos and hence the thermal history of the universe. And I've got some references at the bottom of this slide if you ever needed to look into that. But the bottom line is this sort of relationship between smallest halo mass and mass of warm dark matter particle gets changed slightly by a factor of order unity for sterile neutrinos. So these figures we've got are sort of essentially amplitude of perturbations as we sort of saw before in structure formation, co-moving wave numbers on the bottom, corresponding mass scale on the top, going from huge masses on the left over to small masses on the right. And the solid line is standard CDM. And so you see that this is biggest on small scales. So it's the small halos that form first with bigger things forming later. And then these dashed and dotted lines are putting in the cutoff in the power spectrum from the erasure of density perturbations for warm dark matter for three masses, 1 keV, 3 and 10. And then this other box on the right here zooms into the interesting region where we're seeing the effects of the warm dark matter. And in particular, we see with 10 keV warm dark matter, so actually, no, I've got it the wrong way around. I should be focusing on the 1 keV. With 1 keV, you'd end up with this sort of cutoff kicking in here around 10 to the 12 solar masses, whereas in fact, we know there are loads of small dwarf galaxies that are smaller than that. So just the fact that those small dwarf galaxies exist tell us that this light, a warm dark matter candidate, is already ruled out because we wouldn't be getting the dwarf galaxies we observe in the universe formed. On the other hand, if you sort of take it down up to 10 keV, the cutoff mass scale decreases and gets to the point where it could be consistent with data. And we'll talk a bit more about that later. So let's have a look at what happens to the dark matter distribution in simulations when you have warm dark matter rather than cold dark matter. So these are plots from this review paper. On the left, we have a simulation of a Milky Way-like galaxy with standard cold dark matter. And so we're seeing the huge amounts of substructure that we've already seen before. On the right is the same thing, but for warm dark matter instead. And even just looking at these two plots by eye, you can see that there's a lot less substructure in the form of subhalos in the warm dark matter case. And this is quantified in the plot below on the right-hand side. So these plots contain three cases: cold dark matter, self-interacting dark matter, and warm dark matter. And we'll come back and look at the self-interacting dark matter case later today. So this is number of subhalos quantified in terms of Vmax, the maximum value of the circular speed. And as I sort of mentioned briefly, I think yesterday, Vmax is a good practical proxy for the mass of a halo. The bigger Vmax is, the more massive the halo. And the solid line is what we saw yesterday for sort of CDM. So we've got lots and lots of substructure. As you go down to smaller masses, you see more and more subhalos. And then here we're wanting to look at the sort of paler sort of small dashed line, which is for warm dark matter. And so you see there's this significant suppression in the amount of subhalos. And in particular, it gets bigger the smaller you go. The other thing we're interested in is the density profile. And in this case, it actually, the warm dark matter line is indistinguishable from the CDM line. It seems that certainly in Milky Way sized halos, warm dark matter doesn't affect things. There are arguments that in some cases you would expect a core, because warm dark matter would typically be a fermion, and hence there's a limit to how tightly you can pack them into phase space, and so you can't get high central densities. But in fact, that's sort of not something that actually ends up causing a visible effect in Milky Way sized halos. So actually, yeah, before I go any further, let's just pause here. I've talked about what we expect theoretically from simulations. What I'm now going to talk about is the observational probes, but let's pause for a second in case there's any questions about the theory.
Questions? Yeah.
Just a clarifying question. These plots you're presenting, or a couple slides before, but these are all findings that you have from simulation, or is there a more analytic, or are you driving these analytically? That wasn't clear.
So sorry, which plots are you referring to here? The ones on this slide? So is it the two plots on
analytically solved?
So what I'm trying to clarify is, which plots are you asking about? The ones of the power spectrum or the ones of the density profile and subhalo mass function?
These plots here, particularly the bottom
These plots.
left one.
So these don't come from these massive M-body and hydrodynamical simulations. It's not fair to say they're purely analytic either. To a study, you can't do the evolution of density perturbations purely analytically. So you need a Boltzmann code that solves for things. So they're numerical in the sense that they come out of evolving differential equations, but they're not numerical in the sense that they come out of these massive M-body simulations.
Thank you.
Any other questions? Yeah.
So before, you made a distinction between changes like primordial and evolutionary. So the ones affecting perturbations and the ones affecting, like, once the halo have formed, but wouldn't we expect primordial changes to also lead to changes in once halos have formed? Don't we expect these changes to happen, both changes to happen?
So I'm afraid I didn't manage to get that question. Perhaps could somebody paraphrase it? It was the question about expecting changes to the density profile.
Maybe you just ask again.
Yeah, it was before you were making a distinction between primordial or evolutionary deviations from vanilla cold dark matter. But as if they were yeah. But don't we expect, if we have primordial modifications, to also have this evolutionary modifications?
Yeah, no, you're absolutely right. There isn't a sort of clear cut, it's either this or that actually the primordial will then lead to evolutionary deviations. But I guess the distinction that they're trying to make is that there are some deviations which are purely evolutionary, in that even if you didn't change the initial mass function, you would then still get deviations. So you're absolutely right that this is sort of a hand wavy thing that isn't perhaps as clear cut as it might initially seem.
Anything else? Okay, I don't see anything. All right, so please go ahead.
Okay, so we'll now have a rapid sort of whistle-stop tour on sort of observational constraints on warm dark matter. And in particular, we're going to be looking, the changes here seem to be sort of mainly coming from the happening to the halo mass function. So we'll concentrate on that. And actually, this first constraint I'm going to talk about isn't so much the halo mass function, but actually on the linear power spectrum, as in looking for the effects of this cutoff. And so the first thing I'll mention is what's called the Lyman alpha forest. So if you look at the spectra from galaxies and quasars, there turns out to be this forest of spectral lines. And they come from the Lyman alpha, so N equals 1 to 2, transition of electrons in neutral hydrogen gas along the line of sight. And the different gas clouds along the line of sight are at different redshifts. So this is hence where you see this line repeated in different wavelengths. And so what this allows you to do, and in particular, the depth of the lines is telling you the transmission probability and hence the amount of matter in the clumps at different redshifts. And so what it then allows you to do is probe the power spectrum. And then hence you can do it on a scale where you end up being sensitive to this cutoff from you would get from warm dark matter. So this is a plot of the matter power spectrum as a function of co-moving wave number K again. And there's data, lots and lots of different data sets, but roughly what's happening is as you go up, you're going to higher and higher redshifts. And then the solid lines is in green, we've got the best fit for vanilla lambda CDM. And then in red, you've got what you would expect if you had warm dark matter with a mass of 2.5 keV. And so you can see at small k or equivalently large length scales, the theory curves are absolutely identical. But if you go to the right of the plot for large K or small length scales, you're seeing a suppression in the power spectrum for the warm dark matter. And so by comparing what you measure from observations with the expectations from warm dark matter, you can constrain the mass of the warm dark matter. i.e. if it's too light, it's moving too fast, it erases too much structure, and you wouldn't be seeing the points you see out here on the right of the graph. And so again, these results tend to get quoted for a simple thermal relic, but there's a scaling you can use to apply them to sterile neutrinos if you want to. And the latest analysis here is that you get a limit on the mass of warm dark matter that it has to be more than something in the range of 3 to 5 keV. And the uncertainty here is, as you can probably tell from this plot, this is a really messy thing to do. And these constraints tend to be done by people who are experts on numerical simulations, because you have to do numerical simulations of the interstellar medium to be able to do this analysis and interpret it. There are other sort of more intuitive ways of probing warm dark matter, and most of these then we're looking more directly at the subhalo mass function, i.e. how many small dark matter halos there are. And so one way of doing this is you can do it in the Milky Way, and you can compare the predictions for the abundance of dwarf satellite galaxies from simulations, trying to take into account the baryons and which of these small subhalos are going to light up and form a dwarf galaxy, and then compare it with observations. And as I've already said, with the observations, you need to take into account the fact they're not complete, that we're not seeing all of the dwarf galaxies that exist, because you can't look in every direction, and some of them are going to be very faint and very distant. And I think I won't try explaining this plot in great detail. It's a plot of the fraction of simulated Milky Way-like galaxies, simulated assuming warm dark matter, which have at least as many satellites as you infer in total for the Milky Way. And the bottom line is you end up with a constraint on the warm dark matter mass that it has to be greater than about 2 kiloelectron volts, because if it wasn't, you wouldn't have enough small dark matter halos to form all the dwarf galaxies we see. So this is almost, flipping the satellite crisis on the head, as in saying, well, what do you have to do to make sure there is as much substructure as is actually observed? So then coming on to tidal streams. And so this is possibly a more new sort of technique that's really only being developed. And so what's useful here is very thin tidal streams of stars. And what then happens is if you have a sort of fairly chunky subhalo that comes close to a stream of stars that were initially all moving with very similar speeds, that subhalo is going to gravitationally perturb the stars and give them a kick. and it's going to mess their orbits up. And the net effect is you end up with a gap in what would otherwise be a nice continuous stream. And the theory is that that sort of gap should be observable if your subhalo mass is greater than about 10 to the 5 solar masses. So in principle, at least, this is a nice way of probing the masses of subhalos going down to things that are smaller than dwarf galaxies and that we don't expect to form stars and be visible with a telescope. So this is a picture of a particular tidal stream, GD1, and I must admit, I don't know where that comes from. There are other tidal streams, like one from something called PAL5, and PAL5 is a globular cluster, a sort of cluster of stars that's being torn to bits. Whereas as far as I know, GD1, no one's figured out exactly what the original object that it came from was. Not that that matters, that's just an aside. So this is the results of actually trying to do this analysis and constrain the amount of subhalos there are. And again, it's a sort of pretty complicated figure. What's being plotted here is the density power spectrum of the stars in this stream and sort of how they're correlated. And the idea is by looking at that, you could sort of, this is how you would practically find a gap in the stream from subhalos. The plot on the left, so we've got the data with error bars when they calculate the power spectrum from the observations, and then the sort of expectations in the shaded things. That is what you would expect if the only clumpiness in the Milky Way halo is the baryonic structures we see, i.e. the dwarf galaxies that we know are there. The plot on the right, and you see you've got this mismatch between observations and theoretical expectations. So this seems to be telling us that there's more dark substructures in the Milky Way halo. And so when you add in dark substructures, as you'd expect from CDM, you then end up with this matching. And so again, if you had warm dark matter that was too light, it would erase perturbations and you wouldn't get small dark subhalos forming, but we need them to explain these observations. So again, they end up with a constraint that warm dark matter has to be more massive than about 4 or 5 keV in order to explain these observations. Then we come on to strong lensing, and there's two ways that strong lensing can tell us about subhalos. The first one is a sort of traditional thing that's been going on for a while. The second one is a new one. So first up, we have flux ratio anomalies. So we talked about strong lensing back at the beginning of my lectures. And so this is the classic case where you get multiple images due to sort of lensing by something massive intervening. And if you can work out where you expect these images to be and how bright they should be if the distribution of matter in the lens is smooth. However, what flux ratio anomalies are a case where actually the fluxes, i.e. the brightness of different images, doesn't match what you'd expect from the dark matter being smooth. And in this particular case, apparently, this image here, labeled B, should be the brightest of this trio of images A to C if the dark matter was smooth, but it is in fact the dimmest. And so you can sort of explain that by the dark matter in the lens not being smooth, by there being substructure. And again, you actually don't have enough substructure to do this if the dark matter is warm. And again, we're getting a limit out that it has to be more, warm dark matter would have to be more massive than about 5 keV to explain this observation. So then the new thing, or at least it was new to me, is what's called gravitational imaging. And in this case, it's not looking at the statistical effects of subhalos on the lenses or anything else. It's actually trying to sort of image them more directly. And so what's happening here is if you've got a sort of a dense substructure, it can change the shape of the images you're seeing. And the case where this is most sort of observable is in these long arcs that you sometimes get in strong lensing systems. And so in this case, the lens is a luminous galaxy, so you can actually see it directly as well as seeing its effect on the long arc. However, you can do the same thing for dark lenses. You then wouldn't see the lens itself as the visible object, but you would detect that it was there by looking at the effect it had on the long arc. And so people have done this with multiple systems like this. And at the moment, the constraint is quite weak. It's only that the warm dark matter has to be more massive than 0.2 keV. So that's weaker than the other limits we've looked at. But the point being here is that I think this is a new technique, and that with better data, there will be better constraints. So then this is results from a paper that did a joint analysis. We won't go through this in any detail. What this table, I'm showing it to you to get across the point, is that lots of people are working on observational constraints of warm dark matter. There's a long list of references. There's a bunch of different methods that I've sort of, most but not all of which I've tried to just briefly talk you through. And then the results are in the final column. And these different methods and different particular implementations of them find slightly different results, but there is sort of clearly a consensus that thermal relic warm dark matter has to be more massive than about 5 or 6 keV, because otherwise we wouldn't have small dwarf galaxy-ish size subhalos forming, and we need them to be consistent with these various observations. So yeah, that is all I had to say on warm dark matter. So any questions at all on the theory or observational constraints on warm dark matter?
Oh, go ahead.
Yeah, if you go back to the slide a few slides ago, where you plotted some error bars with, I can't remember exactly, a couple of slides, yeah, this one, sorry, this one. So I understand, like, it seems to me that both plots, the error bars in the first plot are very, very large, and I guess only 1 sigma, so I don't understand how the observations are both consistent and not consistent with there being dark matter. It's not halos.
Right, so I must admit, this is not a technique that I've looked into in any detail. You are absolutely right to sort of get suspicious of error bars, which are so big and then clearly correlated. All I can say is that it's clear that with the only baryonic substructures, that actually that's not consistent, in that typically the theory is lying underneath all of the data points. Whereas if you then add in dark substructures, the theory comes up to be broadly consistent with the data. But I have not looked under the hood of this paper to see exactly how they reach the conclusions they do.
Thank you.
Anna Catherine?
In the plot that you showed for the Milky Way satellites, this is just a basic question. Can you help me understand how to read it, or repeat what you said about how to read it?
So in fact, I decided on the fly not to explain this figure, because I really struggled in this case to find a figure that conveyed what was going on. And at the time I wrote this lecture, I thought that this was the best one I could find. I then sort of wasn't convinced about it. I will maybe try and do that explanation now, but let's see. So what these people did was simulate a whole bunch of Milky Way-like, well, they looked at a whole bunch of Milky Way-like halos coming from warm dark matter simulations. And the reason why you can't just do it for one is that there's statistical scatter. You'll get different numbers of subhalos and different parent halos. So you have to do it for multiple ones and take that into account. So what this is then calculating is the fraction of the simulated Milky Way halos they looked at that have enough substructure to be compatible with what's observed in the Milky Way as a function of the mass of the warm dark matter. And so the different curves are, I think the grey one is taking into account the scatter between different parent halos, and then I think the purple one is then taking into account uncertainties in the observations. And so the bottom line is, if they say that if you had warm dark matter that is more massive than about 3.5 Kelvin, then all of your simulations have enough subhalos to be compatible with observations. On the other hand, if it was as light as 1.5 keV, none of them do. And then the way they set their constraint is to be very conservative and look at the case where 95% of their halos, simulated halos, contain enough substructure. And the result there is that this is where this 2 keV limit comes from, that provided the warm dark matter is more massive than 2 keV, 95% of their simulations have enough subhalos to be compatible with the observations. But the bottom line is what they're basically trying to do is quantify a by-eye comparison between a simulated warm dark matter halo and what we observe in the Milky Way.
Okay, that helps. Thank you.
Yeah, Max.
I'm not sure I'm understanding the Lyman alpha forest. So I guess I understand that we have these gas clouds at different redshifts, and we're gauging how much mass there is based on how much of the depletion in the flux there is. But when we look at these sources, aren't we kind of gauging all the substructure that's in between us and the source we're looking at? So I guess I'm wondering, how are we setting definite constraints on the subhalo mass function when we're looking at everything in between?
So in this case, it's the primordial power spectrum rather than the subhalo mass function that's getting constrained. And what you said to start with matches entirely my non-expert understanding of this. And so I must admit, when I came to writing these slides at Nottingham, we've got somebody called Jamie Bolton, who's an expert on these sorts of simulations of the ISM. And so I asked him about this, and he sort of suggested, for instance, these references. But essentially what you've said matches my understanding of how this works, but just with the caveat, it's not the subhalo mass function that's directly being probed in this case, it's the power spectrum as in this plot here. And exactly how that is done is basically there are teams of people who have spent many years working on doing this. So it's a case where it's difficult to come up with a simple intuitive explanation of how this is done, but this plot is the results of doing it.
Arman, you had a question? No. Oh, I thought you had a hand up. Anybody else? Oh, yes, Andy.
Yes, I have a question on the previous slide, right, also the slide 2. I mean, how do you get the redshift? I mean, are the places you're looking just in different parts of the sky, and so if you just know the distance to these, I guess these galaxies or quasars?
And that's what I'm afraid I'm just going to have to say. I don't know how they do this, in the details of this in practice.
Anybody else? I think nobody, and the chat is also empty. Okay.
Okay, so now let's come on to self-interacting dark matter. So I think the original idea for this is due to Spergel and Steinhardt mostly. And actually, this was then motivated by the sort of appearance of the sort of small-scale crisis for standard CDM in the late 1990s. And if you want to know what the current situation is, then of the references I mentioned at the beginning, the LSST Dark Matter Group white paper is really good. And then there's this Tullen and Yu physics reports, which focuses entirely just on this topic. So self-interacting dark matter is the case of when you've got dark matter particles elastically scattering with each other, with some cross-section that is sort of bigger than one might naively expect. And one can, in this case, do some sort of hand-wavy things to get a handle of what's going on. So the rate at which these interactions would happen is going to be given by the number density of the dark matter times the interaction cross-section times the relative speeds. And so this is just the flux at which things get close enough to each other to interact. Number density is mass density divided by mass. And then if you put some sort of characteristic numbers into this expression, you get some fraction 0.1 per gig a year, sort of normalizing to typical densities of astronomical objects, typical relative speeds, and then a benchmark cross section, which is the sort of value at which effects become observable, of 1 centimeter squared per gram. And so with that sort of interaction in the range of, say, 0.1 to 10 centimeters squared per gram, you can sort of work out that the mean free path between interactions, i.e. the distance that a dark matter particle travels between interactions with another dark matter particle, ends up to be something of order a kiloparsec. And so these interactions mean that instead of just interacting by gravity, the dark matter is interacting with itself. And so you can get what's called thermalization. And so the upshot of this is that you can end up with a constant density core in the inner regions of dark matter halos. And we'll sort of look at more at the consequences of that in a moment. And so one thing to sort of just emphasize here, when people sort of look at observational constraints, they'll typically consume that sigma divided by m, i.e. the cross section divided by the mass, is just a number. But when people then construct specific particle physics models, for instance, dark photon is one, you end up with this quantity being velocity dependent. So it actually is a function of the relative velocity. And then consequently, what that means is it can have different values in the early universe to today. So if you have constraints that look like they're incompatible, actually maybe they're not in a concrete model where the interaction cross-section varies with velocity. And then we're going to be mainly doing what people mainly do, which is looking at the evolutionary effects, i.e. how the individual interactions of the dark matter particles lead to changes in the density profile. However, there can also be sort of primordial effects here, and that in a concrete model, it's hard to set something up where the dark matter just interacts with each other. It's also going to interact with other things. And the net effect of that will be, again, to suppress the power spectrum of the density perturbations on small scales, and hence to affect the mass function of things. But that's not something I'm going to talk about here, because the papers I'm drawing heavily on don't do it. But it's if you did go to a concrete particle physics model, there would then potentially be these additional effects in addition to the things I'm going to tell you about. So back here we are to these sort of figures of what we're expecting. So on the left at the top still, we've got Milky Way-like halo simulated with cold dark matter. On the right, we've got a self-interacting dark matter simulation. So in this case, what we're seeing is visually, in terms of substructure, the two look very similar. So if we look at the plot on the bottom right of the sub-halo mass function, what we see in this case, CDM is the dark line, self-interacting dark matter is the darker dashed line, and they're incredibly similar. So the simple case where you're just considering the effects on halos once they form, self-interacting dark matter matches cold dark matter. Where we see a difference in this case is that we just talked about these interactions lead to thermalization in the central regions of halos, and hence we're ending up with a constant density core in the self-interacting dark matter case on the left-hand side. So again, that's the theory. Now let's have a look at observations. So we come back to an old friend here, the bullet cluster, and the standard sort of constraints, well, evidence for dark matter from the bullet cluster comes from the fact that weak lensing tells us that most of the mass is centered around the galaxies, that this cluster and the subcluster have passed through each other. The galaxies and the dark matter pass through each other, but the baryons get hooked up in the middle. The dominant component of the baryons, the hot X-ray emitting gas, gets hooked up in the middle. If the dark matter isn't collisionless, if it interacts with each other, the dark matter can lag behind too. And in particular, self-interactions of dark matter would transfer momentum between the halos around the different clusters. And so the dark matter would also end up lagging behind. Not as much as the hot X-ray emitting gas, but nonetheless, you would expect an offset from where the galaxies are. And so when people actually do this, you sort of look at the lensing contours, and if there is an offset between the dark matter and the galaxies, it's pretty small. And then there are sort of apparently, and I'm absolutely not an expert on this, a bunch of other constraints on self-interactions of dark matter from these merging clusters. If dark matter interacts too much with itself, you sort of destroy the clusters, and you get mass loss, so that you end up, the mass is reduced relative to the luminosity and it doesn't quite match up. And then self-interacting dark matter can also apparently be probed using minor mergers, as in this merger is sort of fairly significant one. The small thing isn't much smaller than the big thing, but you can also get constraints from mergers of a big thing with smaller things. Also, you can have a look at sort of measurements of density profiles of things, and actually try and sort of measure the size of the constant density core that you would expect to form. And I think Anna Capita is one of the co-authors on this simulation paper. So this is something that if you've got any detailed questions, she will be much better qualified to answer them than me. So it's sort of useful general knowledge thing: when people do phenomenological fits of density profiles taking into account a core, the profile that tends to get used is this Burkert profile. It's very similar to NFW at large radii. At large radii, rho goes proportional to r to the -3, so you sort of get what you expect there, but then it's a modification at small r, so that when r is less than rb, you end up with a constant density. And so this plot then is looking at what you would expect for this core radius as a function of Vmax, the peak circular speed that's a proxy for the mass of the halo. And so this is sort of results of simulations, and we go on the left from Milky Way size things, going up on the right to bigger cluster size things. And so what you're seeing is, in this case, with self-interacting dark matter, you can get constant density central cores in really quite big dark matter halos, not just Milky Way sized ones, but going out to cluster sized ones. And so, perhaps possibly unsurprisingly, what this plot is basically telling you is the bigger the system, actually, the bigger the size of the constant density region you end up with. Another thing that self-interacting dark matter affects is the shape of halos. And so this is something that I didn't actually talk about yesterday when talking about expectations for vanilla cold dark matter, because it wasn't directly relevant to the things we were interested in yesterday, which is how the dark matter is distributed, the aspects of that are relevant for dark matter detection. But what it turns out is that actually cold dark matter halos aren't perfectly spherical. They're actually what's called triaxial, as in there are 3 axes and no 2 of them are the same. They're all slightly different. So they're like the case on the right here in green, the triaxial one. So now, having briefly met what the standard CDM case, let's have a look at what happens with self-interacting dark matter. And it's these self-interactions isotropize the dark matter particle velocities. So in a triaxial halo, the orbits of the dark matter particles aren't isotropic. The components of the velocity in each direction aren't the same. And it's those differences that end up giving you this difference in the shape. However, if you add in self-interactions, the effect of those interactions is to make the velocities more isotropic, and so consequently to make the shape of the halo more spherical. And the shape of the dark matter halo, it isn't just a fixed thing at the edge. Actually, how triaxial things are varies with radius. And so what we end up with here is the theoretical plot of the ratio of the minor axis to the major axis as a function of radius. So we're going out to the virial radius on the right and down to smaller radii on the left. And the black line is what you get for standard CDM. So in the outer regions, you're not so far off being spherical, but in the inner regions, things can be quite sort of compressed in the sort of short axis. The blue line is what you expect theoretically in simulations from self-interacting dark matter, with this benchmark cross section of 1 centimeter squared per gram. And so you see not too much of an effect in the outer regions, but in the inner regions, you end up with the dark matter distribution spatially being much more spherical than it would otherwise be. And I guess the other thing I need to say about this plot is it's for sort of roughly Milky Way and slightly bigger mass galaxies. So that's the theory. How would you probe this observationally? Well, strong lensing, in particular of galaxy clusters, probes the shape of dark matter halos. And so this is then sort of how you would then constrain the shape, and hence whether dark matter's standard vanilla cold dark matter or these self interactions. And I've not gone into the details of this because you can probably get the impression that perhaps this isn't as clean a test as some of the sort of other things. So here is a compilation from the Tullin and Yu review paper of the status of constraints and observations of self-interaction circa 2017. But when I did a trawl through the literature, I couldn't find any significant changes in this. I'm sure these things have been refined, but no sort of completely different constraints. So at the bottom of this table, we have constraints from the shapes of halos, i.e. the thing I've just talked about, and then things from merging clusters, including the bullet cluster. And so what you sort of typically see is you end up with constraints on how big self-interaction can be, then it's got to be less than of order a centimeter squared per gram. And then the next column here is just telling you what the relative velocity of the particular systems that have been looked at are, and then what exactly the observation was, the references from this paper to go looking at them. The top of the table is what they're dubbing positive observations. And so in this case, let's sort of take the sort of potential challenges for standard cold dark matter and how big would the self-interaction cross-section have to be to then resolve these challenges if you sort of take them at face value. And so, for instance, the top one is from galaxy rotation curves, this indication that perhaps there are constant density cores in spiral galaxies. If you have this cross-section of order a centimeter squared per gram, then you could get a central density core and explain this. There's the too big to fail problem that I mentioned, this sort of perhaps why aren't there as many moderate sized galaxies as perhaps you predict in CDM. Cores in clusters, so central density profiles in clusters, and then some potential hints of offsets between dark matter and galaxies in various mergers. And so again, as I really want to try and emphasize, this is not an area that what I work on. I'm trying to overview a vast range of topics in these lectures. My impression is that these things are sort of tentative hints of possible discrepancies that could be explained by self-interacting dark matter, but there's no real sort of smoking gun clear-cut thing. This is definitely an issue that has to be explained. So there's possibly self-interacting dark matter helps make theory and observations consistent, but I think this is one of those things where at the moment the jury is definitely still out, that, this is a field that's sort of still developing. So then we just come to wrapping up with non-particle dark matter. So any questions on self-interacting dark matter, but with a huge caveat here that this is an area which I don't have a deep understanding of.
Okay, so any easy questions for Anne? Yeah.
I'll repeat some easy question, but I would like just to understand intuitively why this self-interacting dark matter solves the Karpov problem. So is it like on a scale below the mean free path, these interactions lead to a strong pressure support that compensates gravity somehow, or how?
Oh, I don't honestly know whether that's the sort of underlying physics that's going on. It's mainly an energy sharing thing that, the thermalization. And so, yeah, I think I'm just going to have to hold my hands up and say, sorry, I can't answer that one.
Yeah, but Annika Peter, I'm sure you just ask her this question again. She's awesome in explaining it also. Any other questions? Okay. I hope I didn't scare people. Last chance? All right, and nothing in the chat. Okay.
Yes, so no, just to really emphasize here that here I'm really talking about things on which I'm not an expert, but the reason I'm chosen to do it is I wanted to sort of get across to you the concept that astronomical and cosmological observations can probe the nature of dark matter. You know, it's not, you know, as ideal as doing a lab experiment and really directly detecting dark matter. But on the other hand, we don't know what dark matter is. We've got to do everything we can, use any data that tells us anything about the nature. And so it is actually quite interesting, I think, that you can say, learn something about the nature of dark matter via astronomical observation. So really what I'm trying to do today is just make you aware that this is a thing, that you can say something about dark matter, whether it's warm or whether it's self-interacting via astronomical observations. So let's then skip to the very end. So everything I've talked about so far sort of assumes that dark matter is some sort of new particle of one form or another. However, that doesn't actually necessarily have to be the case. And so one particular sort of concrete example of a form of dark matter that isn't a new particle is primordial black holes. And so this is something that I started working on many years ago as a PhD student as a probe of the early universe. And then now in the last sort of 4 or 5 years since LIGO Virgo have discovered gravitational waves from mergers of massive black holes, there's been a huge explosion of interest in primordial black holes as a dark matter candidate. So I'm not going to say too much about this, because Bernard Carr, who's kind of the world expert on primordial black holes, and Florian Kuhnel, who's done a lot of work in the last few years, you're going to be getting some lectures from them. I am a member of Team PBH, but not as enthusiastic about them as these two. I'm a bit more skeptical, but nonetheless, as a member of Team PBH, I wouldn't be doing my duty if I didn't at least sort of give you a flavour of sort of primordial black holes as a dark matter candidate. And in particular, relevant to what I've been talking about today, they're a dark matter candidate where direct detection isn't a possibility, and you have to rely on astronomical observations to try and probe them. So, as Bernard, I'm sure, will tell you in a lot more detail, primordial black holes are black holes that form in the early universe rather than the conventional astrophysical black holes that form at the end of the lifetimes of massive stars. And basically, you can form a black hole in the early universe if you have a large enough overdensity, that simply you get enough material in a small region that it just falls with its Schwarzschild mass, radius, and there's your black hole. There are various ways you can do this, sort of using early universe processes, for instance, bubble collisions from phase transitions, but probably the simplest mechanism is the collapse of large density perturbations. And so these are exactly the same density perturbations that we've already talked about lots on larger scales that form galaxies, galaxy clusters, large scale structure, but just on much smaller length scales. The caveat is, though, that they have to have much bigger amplitude. If their amplitude were as small as it is on large scales, the number of primordial black holes you would form is absolutely negligible. But if they're larger on small scales, and you can construct models of inflation that do this, but it's a bit fine-tuned, you will get primordial black holes forming. Now, famously, primordial black holes, well, any black hole evaporates due to Hawking radiation. So very light primordial black holes would have evaporated by the present day. But provided their mass is greater than about 10 to the 15 grams, then their lifetime is longer than the age of the universe. So they're stable, and hence they're a possible dark matter candidate. And because they form at early times before nucleosynthesis, they are non-baryonic, which is another thing which a dark matter candidate has to have. So again, Bernard and Florian will talk to you about this in great detail, but here is a very rough summary of the observational constraints on the fraction of the dark matter that's in the form of primordial black holes. This is from a review paper I wrote this time last year with Bradley Kavanagh, but there were also sort of review papers, various ones by Bernard and collaborators. And so this is a plot of the constraints on the fraction of the dark matter in the form of primordial black holes as a function of the primordial black hole mass on the bottom axis in solar masses, on the top axis in grams. So we're going from 10 to the 15 grams up to sort of thousands of solar masses. Very light primordial black holes, whilst they won't have evaporated completely, they'll have started evaporating. So there's a whole bunch of really tight constraints from looking at the products of the evaporation in orange on the far left. Coming over to the sort of planetary and solar mass region, here the constraints come from microlensing that I mentioned back in the first section. And so this is the temporary brightening of background stars that occurs when a compact object passes across the line of sight and lenses them. Coming over then to purple, these are actually gravitational wave constraints. And so the thing that triggered the recent wave of excitement in primordial black holes as a dark matter candidate was the observation of gravitational waves from the mergers of massive black hole binaries. It turns out when you then look in detail at the number of binaries you would form if the dark matter was primordial black holes, you would actually, if it was all of the dark matter, you get way more of these gravitational wave events than have been observed, probably, modulo some uncertainties in how primordial black holes cluster. So here you're actually saying that actually if the primordial black holes around a solar mass make up more than about 1% of the dark matter, you get far more gravitational wave events than observed. Then in red, we have accretion constraints because accretion onto the black holes, either today in the Milky Way or at early times, then leads to emission that would be detectable as either X-ray or radio point sources, or it would mess up the cosmic microwave background. And then finally, right on the right of these plots are what are called dynamical constraints. And if the dark matter was in great big massive clumps, dense clumps or point masses like a black hole, bombing around the Milky Way, it would wreak havoc. It would disrupt binary stars. It would mess up the Milky Way disk. So Bernard, I'm sure, will be telling you about this in a lot more detail. But for now, you're sort of seeing that this is, again, something where astronomical and cosmological observations are what place tight constraints on this possibility. And taking the constraints at face value, and there are uncertainties, how big they are, I think we're all still trying to understand. But if we take them at face value, we've got this open region in here around sort of 10 to the 18 to 10 to the 21 grams. And so that's basically asteroid mass. And so that's where it looks like you could have all of the dark matter being primordial black holes. And I think the reason this is an open region is just because it's very hard to probe such light compact objects. And so people who work on primordial black holes, I think our job is to come up with novel new ideas for sort of probing this open region. So before I move on to concluding in general, has anybody got any questions about primordial black holes? And these are questions I should be able to answer.
Yes, Max.
Okay, so I think I have two questions here at least. The first one is I'm interested if there are any ideas on how to probe this open window. And the second is, are we saying on the x-axis here, this is the mass of the average primordial black hole, or how do we know the population? You know, I could say I have 10 to the 18 gram primordial black hole, but there could be a lot of them or fewer of them, or the mass could be spread out.
Okay, I'll answer the second question first because it's the easier one. So this constraint plot assumes that all of the primordial black holes have a single mass. So it's one of those simplifying assumptions. And so if the mass is sort of 10 to the minus 6 solar masses, for instance, then you read up and say the constraint is less than 0.1. As you've sort of alluded to, in any realistic formation mechanism, you're not going to get a delta function mass function. You're going to get some spread in masses. And so when actually seriously trying to look into this, you need to take that into account. And that's actually something I've written papers on. Loosely, at least, the effect of doing this is then if this was instead the central mass of your mass function, the typical mass, what happens is roughly these constraints get smeared out. Individually, they each get a little bit weaker, but any gaps between them get closed. And so at one point, there was potentially a gap over here in the solar mass region where you could sort of squeeze a delta function mass function just in between the constraints. But actually, once you try to do things more realistically with non-delta function mass functions, actually it didn't work. So this is with many things, this is a sort of simplifying headline plot, but if you want to do things properly, then you do need to take into account the spread in the masses. And people cook up models where in fact it's not just necessarily a spread in mass, it's sort of mass function which has multiple bumps. But in my opinion, you end up having to really quite contrive the models to do that. So that was the sort of mass function, what's this plot question. Then the $1 million question is, so what can we do in here in this asteroid mass region? And so in the past, and this is possibly the most promising general type of idea, is looking at the effects of these sort of small black holes on stars, and in particular what happens as a primordial black hole passes through a star. Now, there were at one point constraints that were claimed in this region. For instance, if a primordial black hole of this mass passed through a white dwarf, it would heat it and potentially cause it to explode. There were also claimed constraints on femtolensing of gamma ray bursts. But it turns out that actually, when you get to such light primordial black holes, standard lensing sort of machinery of geometric optics is no longer valid, and you have to sort of take into account quantum mechanical effects. And it turns out that those lensing constraints then go away. You don't expect an observable phenomena. And this is actually what also limits how far down in mass the microlensing constraints go. And so that latter thing about lensing, that's something that Joachim Kopp, who's talking to you later in the school, has worked on. So he will be a great person to talk to about that. So coming back to the stellar constraints, so at the moment, the sort of consensus seems to be that possibly there are some constraints from working out the effects of primordial black holes on individual stars, but it's messy and you need to work out exactly what you were looking for. And so there were constraints that were in here, but they've gone away. There was a fuss, I can't remember quite when, sometime in the last year, Avi Loeb, who is infamous, claimed some constraint on, I think it was the effects on trans-Neptunian objects, so sort of things in the Kuiper belt in the Milky Way. But he fell into a trap that many people have fallen into before, that it turns out that these interactions of compact objects with any given system, you dump energy in, but the first order term in how big that energy changes averages to zero. So you think there's this big effect, but then when you look at it more carefully, there isn't. And hence that constraint also went away. And in that case, that constraint went away very quickly within a few days. So that's trying to condense a lot of information to a short period of time. But those are the sorts of ideas sort of people have had generally for probing this open region.
Andrew, you had a question? Follow-up.
Just a quick follow-up. That was an excellent answer, though. So I guess I'm wondering, when we say on this plot that I have a certain mass, we're fixing the mass, what are we saying about the population of this mass of PBH? I mean, couldn't there be more or less, or do I know the number just from the mass?
So I guess what this plot is saying is, if the primordial black holes all have a certain mass, you're allowed to live in the white regions of the plot, but not in the coloured regions of the plot.
Follow-up?
But when we say they all have this mass, I mean, couldn't that be, there's 1,000 PBHs or 1 million, or, I mean, shouldn't there be some other kind of axis that says how many of these PBHs at a certain mass there are?
So that is what the y-axis is doing, but it's just not couched in terms of number, it's couched in terms of fraction of the dark matter. But we know what the dark matter density is, so if you fix the mass and know what the fraction is, you could then work out the number if you wanted to do so. But of course, if you're going to specify number, you're then going to have to specify what volume you're interested in the number. So that's why the fraction is the more sort of practical thing to talk about.
Of course, that makes sense. Thank you.
Yeah.
Oh, yeah, I have a question on the gravitational wave. So I heard a lot that this, the detections have renewed interest in PBHs, but this constraint comes from not observing black holes at this, at these masses. So could you explain a bit more why the black hole mergers implied that could be PBHs?
So what it is that if all of the dark matter was primordial black holes, or some large fraction in the purple region, based on how we think those black holes would evolve and form binaries, there would actually be too many binaries. So you would actually, it comes from the number of gravitational wave mergers that have been seen. And if all of dark matter was primordial black holes, then assuming our understanding of how they form binaries is correct, you would be seeing thousands of these mergers rather than a handful.
And imply that that's not happening?
And it's, well, no, LIGO Virgo have seen a handful of these events. If all of the dark matter was in primordial black holes of mass around a solar mass, they would be going boom, boom, boom in the sky on a daily basis.
Like the constraint is much better than it was before on this region because of gravitational waves?
So I'm not sure what you mean by better than before. It was a constraint that actually probably we should have all anticipated was going to be there. There's some Japanese people, Nakamura et al., who wrote papers, predicting that you should be seeing gravitational waves from black hole merger events back in the 1990s. But this constraint is something that's been sort of figured out over the last 3-4 years after LIGO started seeing a few of these events. And I guess one caveat I should just put in to expand on my answer. There's two types of constraint here. One from the raw number of individual merger events, and then a second one, which is actually comparable, which comes from the stochastic background of gravitational waves from these events. And so this is the case where you're not seeing the individual event itself, but the collective effects of all of the large number of these mergers would be to produce a background of gravitational waves. And again, that's something that there are observational constraints on. I'm sure Bernard will be telling you all about this in a lot more detail later in the school.
And Katrin?
Thanks. You might have said this and I missed it, but could primordial black holes form as early as inflation? And also, looking at black holes from the astrophysics point of view, are we actually able to determine their age?
Right, so the first question, so anything that gets formed before or during inflation tends to get inflated away by the exponential expansion of the universe. However, primordial black holes could form really early, as in right after the end of inflation. And in particular, there's sort of two reasons to think why that actually is going to be what's going to happen. There's the preheating process I mentioned at the end of inflation, where the inflaton field decays and you start the hot Big Bang. It turns out that process can produce these large overdensities that you need to form primordial black holes. So that process right at the end of inflation could produce primordial black holes. And then the other thing I've sort of alluded to is that you need larger perturbations on small scales than we have on large scales. So what people often do is our primordial power spectrum, instead of it being a gentle power law, you can create models of inflation with a feature in the potential and hence a feature in the power spectrum. So that's one way you can do it. But the other way you can do it is with the primordial power spectrum that just evolves gently with scale, so that it's biggest on the smallest length scales. And in that, if that were the case, then the primordial black holes would be forming immediately after the end of inflation. So I mean, the short answer to your question is that yes, you know, they could form immediately after inflation, but it's at some point between the end of inflation and sort of the subsequent radiation-dominated era. And then I'm trying to remember what the other question was.
Sorry, I shouldn't have asked you once. The second question was, are we actually able to determine the age of black holes?
And I guess by age, you're meaning when they formed. For primordial black holes, there's a link that their mass is related to the horizon mass at the time they form. So with a primordial black hole, if you measured their mass, you could deduce when they formed. Astrophysical black holes, I honestly don't know. And one point I should emphasize here and use this as an excuse to emphasize is that my opinion is the black holes that LIGO is observing the gravitational waves from, those black holes are almost certainly astrophysical black holes rather than primordial black holes. That's not yet been proved, and that's something which hopefully we'll make progress on with future observations, more black holes, so we probe the masses better and we probe the spins of them. But if I had to bet, and I'm quite conservative with my betting, so I tend to vote for astrophysical explanations for things rather than particle physics explanations. If I'm being 100% honest, my gut feeling is that what LIGO is seeing are astrophysical black holes and not primordial black holes. So that wasn't an answer to your question, but it was just something I sort of wanted to get in.
Yeah, that's really interesting. So is there an observational difference between primordial black holes and astrophysical black holes?
Yeah, so this is an interesting question. And so where there would be an observable difference is not necessarily in anything about the individual black holes, but the thing that's probable is actually their spins, and in particular, the spins of the binaries. And I'm struggling to remember off the top of my head because I wasn't expecting to talk about it, how it works. But I think if I'm remembering this right, the primordial black holes tend to have relatively small spins, and so hence that's what you would expect to observe, whereas the astrophysical ones, the way they form from accretion, I think they end up having bigger spins. And this is something I should be able to remember off the top of my head, but I've just been in dark matter review mode rather than in primordial black hole mode, so I've sort of let that slip from my head.
No worries, that's really interesting. Thank you.
I don't see any other. Oh, more. Okay, go. Yeah.
Okay, so I have a question about the mass function. Usually in the literature, people use log normal mass functions. Is there any physical motivation for that?
So I think I have to fess up, I'm not the first person to use a log normal mass function for primordial black holes, but I'm the person who sort of started it being a thing, and I apologize. So what I was doing was people have calculated mass functions expected from particular inflation models, and they've got some width. And this was sort of very early on where people were making claims of how having an extended mass function would be different from a delta function. And I didn't believe those claims. So I was just trying to do a concrete calculation for a mass function to see what the effect was. And rather than going through the whole hassle of calculating things for concrete inflation models. And so I was just looking at these functions and thought, what would be a decent functional fit? And a log normal was a decent functional fit. And I never expected people to sort of take something I'd used for a sort of rough benchmark calculation and turn it into this article of faith. So yeah, log normal mass functions, it's an approximation, it's a phenomenological thing. And if I ever get the time to do some research, which unfortunately doesn't happen very often once you get to my career stage, I want to really get into the guts of the mass function calculations. And there are bits of it that I'm really not convinced that people are doing quite right. I'm not saying that they're doing it wildly wrong, but I just think there's more work that needs to be done to come up with really accurate calculations of the mass function. But it sounds like it's something that you know a bit about, given the question. So feel free to email me afterwards if you've got any more detailed questions.
Yeah, I saw one more hand, I think. Oh, yes.
Sorry if this was already answered before, but there are implications for the CMB spectrum from the existence from EVH?
Yes, so it's, let me, again, this is something I should remember, but I'm just getting fuzzy on the details. I think it's not the angular power spectrum, but actually the spectrum and distortions of that actually are the thing that's best constrained. But off the top of my head, this is something where I'll check and I'll stick a better answer on the sort of Padlet website later in the day. I'll get back to you on this one.
Okay, so no more hands in the lecture hall, but there is one question in the chat. So Josef, do you want to just unmute yourself?
Yes, thank you. So maybe, can you hear me?
Yes.
So maybe I'm missing something here, but let's imagine that these primordial black holes have this mass of the asteroids or small planets, and they constitute the dominant part of the dark matter content. Then how does it fit to this concept of, for example, a Milky Way halo, which is like sitting around our galaxy and then does not have much of dynamical effects on how I cannot imagine having like asteroid like black hole dark matter particles and then just sitting around our galaxy as this dark matter halo that we imagine there is. So how does this fit how does these two things fit together?
Okay, so broadly at least, you would have primordial black holes flying around sort of a couple of 100 kilometers a second, all sorts of directions, in exactly the same way that microscopic particle dark matter would. But you're sort of right in that there's this is very different to sort of there being an essentially smooth dark matter distribution with sort of clumps from subhalos in it. We're then dealing with a dark matter distribution that's very granular, and so the fact that if it's too granular, you end up with these sort of dynamical effects is what then puts these constraints. And so I guess sort of asteroid mass things are actually, they're quite puny, and so it turns out that they're much actually harder to track down than you would think they are. And if you are sort of interested in constraints on dark matter being compact objects, there's a review paper, it's quite old, but by Berniccar and Mary Sakellariou, where they look at every possible way you could possibly constrain sort of physical sort of size of dark matter objects, and it just does turn out that actually asteroid mass things tend not to have many effects.
Okay, thank you. And then also I had one question about the mass range that you showed, like this 10 to the 15 grams up to 1,000 solar masses. This is really from the plot that we see that the boundaries are ruled out by this evaporation and accretion, so we don't need to extend the range.
So the 10 to the 15 grams at the lower end is absolutely because anything lighter than this will have already evaporated. Whereas one of the things we know about dark matter is that it has to be stable on cosmological timescales. It has to be here in the universe now. So that lower limit is pretty robust. The upper limit, I've stopped this particular plot at 1,000 solar masses as simply a sort of credulity thing. Bernard is probably going to be showing you plots that will go up to what he calls slaps, stupendously large black holes. And I think that is sort of ruled out, not least because we know there are dwarf galaxy-sized dark matter halos. And the dark matter mass cannot be large compared to a dwarf galaxy, as in dwarf galaxies would not sort of behave as they do if the dark matter in them was sort of 10 to the 4 solar mass objects. And I think this is essentially the argument you were making with asteroid mass ones, but whereas I'm convinced by it once we get out to sort of 10 to the 3, 10 to the 4 solar masses. So that is a sort of personal rough cutoff that I've put on this plot, but I think it would be very difficult to go above that. And as you're already seeing, there are these sort of, really tight constraints already kicking in at 10 to the 3 solar masses.
Great, perfect. Thank you.
So I guess what I should probably do now is actually get to the end. So let's do that. So summary from today, at least. And so, as I keep emphasizing, today I've been talking about things in which I am absolutely not an expert, but what I wanted to do was get across to you that astronomical and cosmological observations don't just provide evidence for dark matter, they can, when combined with the results of numerical simulations, probe the nature of dark matter. And so we looked at self-interacting dark matter, which is potentially interesting because it produces constant density cores in halos, and this is something there's some evidence for from observations. We also looked at warm dark matter, which has a different effect, that you end up not getting small subhalos. And in fact, in this case, you end up with limits on the mass of the warm dark matter. And then right at the end, I opened up the huge can of worms that, dark matter doesn't have to necessarily be a particle. And we looked very quickly at how observations constrain dark matter in the form of primordial black holes. To summarize everything I've told you this week, so going right back to the beginning, the lambda CDM cosmological model seems to be a good fit to lots of observations. And so lambda CDM, we've got a cosmological constant, and then 25% of the total energy being in the form of cold, non-baryonic dark matter. And this broadly does a very good job of matching all sorts of observations of the universe, nucleosynthesis, the cosmic microwave background, large-scale structure. However, we don't yet know what dark matter is, and we don't know what dark energy is. So if we really want to be sure that we're understanding the universe correctly and not just fitting numbers to a black box, we actually need to go under the hood of the black box and work out what the dark matter is. And so the most sort of direct way of doing this, which you can do for WIMPs and axions and some other dark matter candidates too, is to detect it in lab experiments. And to do that, we need to know how it's distributed in the universe, and in particular in the Milky Way galaxy. And this is very much an area that's ongoing, but the thing I'd like you to take away from my lectures is there's been lots of progress in the last decade in both simulations and observations of trying to understand how dark matter is distributed. And then the thing I've tried to give you a flavor of today is that we can also actually use astronomy again to probe the nature of dark matter, and in particular to look for deviations from just vanilla cold dark matter, which only interacts gravitationally. So I will actually be coming back later this afternoon to do the informal Q&A, but otherwise I hope you all have a good weekend and that you get to enjoy Chamonix and the Alps whilst I'm stuck in England. I hope you enjoyed the rest of the school, and I'm happy to continue answering questions by email or on the Padlet website, so please do continue to ask any questions you've got, but that's it for me.
So I don't know if there are any urgent questions. Otherwise, there will be a discussion session in the afternoon, so you can also ask more questions then. And thank you again, Anne, for a really fantastic set of lectures.